Assalamu alaikum students. Our new chapter is simple harmonic motion, and today we will learn about the topic simple harmonic motion. To understand what is simple harmonic motion, let's see the motion of these objects. Motion of a pendulum, motion of a swing, motion of a ball in a bowl. Did you notice something similar? Yes, all the three objects are moving back and fro about their mean position. So when an object moves back and fro about their mean position, it is called the simple harmonic motion or vibratory motion. Simple harmonic motion occurs when the net force is directly proportional to the displacement from the mean position and is always directed towards mean position. Let's see some examples of simple harmonic motion. The motion of a mass attached to a spring.
Say we have a spring that is attached to some stationary surface, and on the other end of the spring there is a block of a particular mass. If we pull this block so as to expand the spring, and then we release the block, it will vibrate back and forth between more compressed and less compressed states. If we assume that the surface of motion is completely frictionless, then the elastic potential energy reaches a maximum when the spring is most or least compressed and the block is changing direction, while kinetic energy is at a maximum when the block is right in the middle and moving the fastest. If we were to graph the position of the block against time, it would display sinusoidal behavior, just like a trigonometric sine function, where the block continues to occupy the same positions over a particular period of time, which is why we call this periodic motion. X equals 0 at the equilibrium position of the block, where it sat before we pulled it, and assuming zero friction, the block will oscillate between positive x and negative x indefinitely. In reality, frictional forces will dampen the spring's activity, and it will eventually come to a stop. But for many systems, an ideal mass spring system will be a decent approximation for a real one. Of course, every spring is different. Some are loose, like a slinky, and some are stiff, like the spring that launches a pinball into play. This factor is represented by the spring constant K, which will be unique to a particular spring. The force that a spring can exert is equal to negative K times the displacement of the object it acts upon, and this relationship is called Hooke's law. The negative sign indicates that the force of the spring is always opposite the direction of the movement of the object. When the object compresses the spring, it will push out, and when the object stretches the spring, it will pull in. In both cases, the spring is attempting to move the object back to its equilibrium position, which is why the force applied by the spring can be called a restoring force. The units on a spring constant will be newtons per meter, so that when you multiply by some distance x, you get the force that must be applied to compress that spring that far.
We can use the following formula to find out the time period of a mass attached to a spring, where t is for time period, 2 pi is the constant, the value of pi is 3.14, m for mass, and k is for the spring constant. Example number 2 is a ball in a bowl. The motion of a ball in a bowl is an example of simple harmonic motion. When the ball is at the mean position O, that is at the center of the ball, net force acting on the ball is 0. In this position, weight of the ball acts downwards is equal to the upward normal force of the surface of the ball, hence there is no motion. Now if we bring the ball to position A and then release it, the ball will start moving towards the mean position O due to the restoring force caused by its weight. At point O, the ball gets maximum speed and due to inertia it moves towards the extreme position B. While going towards the B, the speed of the ball decreases due to restoring force which acts towards the mean position. At the position B, the ball stops and then again moves towards the mean position O under the action of restoring force, and this to and fro motion of the ball continues. A simple pendulum also exhibits simple harmonic motion. It consists of small bob of mass m suspended from a light string of length fixed at its upper end. In equilibrium position O, the net force of the bob is 0 and the bob is stationary. Now if we bring the bob to extreme position A, the net force is 0. When we release the pendulum, the gravitational acceleration caused by its weight pushes the pendulum towards the mean position. At O, the pendulum doesn't stop on the position O and continue its journey towards the position B. On reaching position B, the speed decreases and due to restoring force, the pendulum starts moving towards the mean position O. At the position O, due to inertia, the pendulum can't stop. That's why it continues its journey towards the next position A. And this back and fro movement continues. We have the following formula for the time period of a simple pendulum. T is equals to 2 pi under root L over G. T is for time period, 2 pi is the constant value, pi's value is 3.14, L is for length and G is for the gravitational acceleration. Time period of a pendulum is the time to complete one cycle. For example, it is the time taken for a pendulum to go from position A to position B and back to the position A.